Hello again. In this video, I'm going to go over this homework problem from 4.3. So in this problem, we're supposed to locate the critical points for this function on this domain from -5 to 8. That's part A. Part B, we're supposed to use the first derivative test to locate the local maximum and minimum values. And then part C, we're supposed to identify the absolute minimum and maximum values of the function on this interval from -5 to 8. Okay, so let me show you how to do this. So for part A, we're supposed to find the critical numbers for this function on this domain. So remember, to find critical numbers occur when the first derivative is either 0 or when the first derivative does not exist. So we're going to look at both of those cases. Okay, so let's find the first derivative. All right, so the first derivative here would be 6x squared plus 6x minus 120. And then we're going to look at the two different cases, when the derivative is 0 and when it does not exist. In fact, let's look at this case first. This derivative always exists. You can plug any number you want in for x, and you'll get a number out, so it exists for all x values. So this never happens. Okay, so we don't get any critical points from this particular case. But let's check this case over here. So let's set the derivative to 0. Now to solve this is a quadratic. And to solve a quadratic, you have to put it in standard form first. And standard form is the case where you have one side of it equal to 0. So this is already in standard form. And then after you put it in standard form, you can either use the quadratic formula or you can factor it. Okay, so here I think we can just factor this. There's a 6 in common, so let's pull the 6 out. And you're left with x squared plus x minus 20. And then you can actually divide both sides of the equation by 6, and that will get rid of the 6 on the left-hand side because it'll cancel out. And then you'll be left with a 0 on the right-hand side. Okay, and then I think we can factor this trinomial. This factors into x plus 5 and x minus 4. And then if you just solve these, x plus 5 is equal to 0. When you solve that, you get x is equal to -5. And when you get x minus 4 equal to 0 and solve that, you just get x is equal to 4. Now, one thing to take note of, in order for you to have a critical point, the critical point needs to be in the domain of the function, and it cannot be at an endpoint. So technically, this -5 is the left endpoint here. So it's not considered to be a critical point. It has to actually be in the interior of the domain. So the only critical point we actually get out of this is the x is equal to 4, because that actually is in the interior of your domain. This is actually not considered to be a critical point. It's actually just called an endpoint. Okay, so for part A, the answer is x equal to 4. Okay? Now, part B, we're supposed to find the local minimums and local maximums on this interval using the first derivative test. So the way the first derivative test works is you take the domain of your function and you break it up into intervals based upon where your critical points are within the interval. So we only have one critical point in this interval, so we're going to break it up. We're going to start at -5, the left endpoint, and then we're going to break that up into this interval where we stop at 4, not including the 4. And then we're going to pick up at 4 and continue on until we get to the next critical number, which there isn't anymore. And then eventually you'll get to the right endpoint. Okay? So this actually breaks up into two intervals, this domain. Okay, and now we're going to check both of these intervals and see whether the first derivative is positive or negative on each of these intervals. And we're going to do that by picking a test point in the interval and plugging it into the first derivative. Okay, so a good test point here might be 0, but you can pick any point in this interval, and you'll get the same sign for the first derivative. It's going to be the same for all of them. So it doesn't matter which point you pick. So I'm just going to pick 0 as my test point and plug that into the first derivative. And of course, when you plug it into the first derivative, you get negative 120. And that indicates that the function is decreasing. Now remember, the derivative gives you the slope of the tangent line at this point. And you can see the slope of this tangent line is negative, and that indicates that the function is actually decreasing at 0. Okay, but again, it doesn't matter what test point you pick in here, you're going to get the first derivative to be negative. Okay, so we know the function is decreasing here in this interval because again, the first derivative is negative in this interval. Okay, now let's pick a test point in this interval, like 5 would work. Again, plug that into the first derivative, and let's just see what you get. So plug a 5 into here, so you get 6 times 5 squared plus 6 times 5 minus 120. Okay, so 5 squared is 25, so you get 6 times 25, and then 6 times 5 is 30, minus 120, and then 6 times 5 is actually 150, and so you just get 180 minus 120, which is 60, and that indicates that the function is increasing. Technically, it's increasing when x is 5, but like I said, you'll get the same sign for any test point that you use in this interval. So if I said f prime of 6, I would have also gotten a positive for the first derivative at 6. Okay, so the function's increasing at 5, but we know it's the same sign for any test point, and that indicates that it's increasing for all points in here. Okay. Okay, and now we're supposed to find the local maximums and minimums from this. Now this is called the first derivative test. When you create this little sign chart to determine where the function's increasing and decreasing, this is called the first derivative test. And so now let's find the local mins and maximums from this. Okay, so you can see here the function is decreasing on this side, right? So it's going down. And then on this side, it's going to increase. So it's going to go back up. And it has to make that transition. Now, it can make that transition in one of two ways that is relevant here. One way it could make that transition is it could decrease like this and then just abruptly start increasing. If that were to happen, then the derivative at this point, let me call it c. If that happens, the derivative at that point doesn't exist. The derivative does not exist at sharp points like this. Okay. The other way this transition can happen is it does it very smoothly, where it decreases and then doesn't come to an abrupt change, but it gradually starts to get to the point where it's going to increase. If it does it real smoothly like this, then the derivative at this point is actually 0. Okay, and this is actually at 4, right? This point right here is at 4 in between. That's where it makes that transition. Okay, so we know the derivative here is 0 because we set the derivative to 0 to get this point x equals 4. Right? I mean, if you plug a 4 back into the derivative, you're going to get 0 out. Okay, and so we know it's decreasing and increasing. It's decreasing on this side and then starts to gradually get to the point where it increases in a very smooth way, not in an abrupt way. Now, if we had the case here where we had a critical point from this case, then we would have in that situation a very abrupt change. Okay, but that's not the case here. This is a smooth change. Okay, and just to verify this idea that the derivative is 0 here, this tangent line at this point, the slope of this tangent line at this point is actually 0, right? It's horizontal. Okay, whereas over here it doesn't exist. Okay, so this is the case that we're in. Okay, it's doing this. And you can see that you have a local minimum when x is 4. Okay. And there is no local maximum. In this interval. Okay. From this first derivative test, the only spot where we have a local min or max is when x is 4 and it's a local minimum. There is no local maximum in this interval. Now, to get a local maximum, it would have to increase and then decrease, right? So it'd have to do something like that. Or if it did it abruptly, it would do something like that. Okay, so we don't have that happening in here. So we don't have any local maximums. We only have the local minimum, and that's when x is 4. Okay, now part C. Now we're going to try to find the absolute maximum y value that this function takes on in this interval, and also the absolute minimum y value that the function takes on this interval. So the way we can do that is we know that absolute maximums and minimums can only occur in one of two places. They either occur at the endpoints of your domain, so in this case -5 or 8, or they have to occur at critical numbers in the interior of your domain, or critical points in the interior. So in this case, if we have an absolute minimum or an absolute maximum, it must occur at -5 or 8, which are the endpoints, or it must occur at the critical point, which is x equals 4. And so all we're going to do now is find the corresponding y values for each of those points. Okay, so we're going to check the endpoints and see what the y values are at the endpoints, and then we're also going to check the y values at the critical points. Okay, and we can do that by, of course, you have to plug these back into the original function to find the corresponding y value. So we're going to plug it back into this function. Okay, so here you're going to find f of -5, f of 8, and f evaluated at 4. Okay, and I'm just going to do that on the calculator. There's actually a very efficient way of doing this on the calculator. So what you can do is you can go to your y equals button and then type the function in. So I've already done that. Type it into y1. So you can see I've got 2x cubed plus 3x squared minus 120x plus 1. So just type the function in. And then go to your window button, because you may have to adjust your window. I've got this window, the minimum x value is -10 and the maximum x value is +10. And just make sure that your domain is contained in this interval, okay, which it is. So -10 to 10, that contains my domain. And then you may have to guess a little bit as to what to make the y min and the y max. It's hard to know what the y values look like for this particular domain. But I've set it at a minimum y value is -500 and a maximum y value at 500, +500. And if you graph this, so next thing is press graph, you can see that it has a pretty good picture of the graph here, right? The window gives you a nice view. So you may have to adjust your window to give yourself a good view here. But after you adjust your window, and you can check the graph of it to see if it's a good window, then what you want to do is you want to go to this calculate button. So it's a second button, and then calc. And you'll get this menu here, and you want to select value. So press enter for value. And then we're just going to, it prompts you for the x value. So I'm just going to enter in each of these x values. So let's start with -5. Now be careful, don't use the subtraction button, use the negative button. So -5, and just enter that in, press enter. And it gives you the corresponding y value. So you get 426 out. Okay? And then I'm just going to do this again, go back to calc, and then value, and then plug in 8 for x, and you get 257 for y. And then plug in 4, go back to calc, and then value when x is 4. Press enter, and you get -303. And in fact, you can see that it actually plots the ordered pair on the graph. Okay. Okay, and then once you find the corresponding y values, all you have to do now is pick off the largest one, and that's your absolute maximum. So this is the absolute max. And then this is the smallest, so that's the absolute minimum. Okay, and let's just double check this on the graph. Our domain is going from -5 to 8. So -5, 1, 2, 3, 4, 5. So -5 is right there. That's where the absolute maximum is. And you can see that it peaks right here. And that's the largest y value on the domain, right? From -5 to, and then 8 would be 1, 2, 3, 4, 5, 6, 7, 8. I believe it's about right there. The y value at that spot appears to be lower, right? That y value appears to be lower than the y value over here. So yeah, that does appear to be the location of the absolute maximum. And then the minimum appears to be right here, right, which corresponds to x equals 4. Right, that's the smallest y value that this function takes on. If you go from -5 to 8, that's the smallest y value right there. Okay, so that does appear to be the absolute min. So you may want to double check on the graph and just make sure it makes sense. Okay, so going back to MyMathLab just to double check this, the critical points we found to be at x equals 4. And we determined that there was a local minimum at 4, but no local maximums. And then the absolute maximum value was 426, and the absolute minimum value was -303. Okay. Okay. So hopefully you found this video helpful. I'll continue to work problems from the homework. And if you get a chance to look at some of those videos in the future, go ahead and do that. Until then, bye-bye.